All right, so we have arrived at Chapter 7, and Chapter 7 has some really awesome applications so that we finally get to see where do we use all of these calculus techniques in the real world. We got one more skill that we have to develop before we jump to the applications, but just as a recap. So in Calculus 1, we developed the technique of definite integration, and definite integration allowed us to, say, find the area under a curve like G, bounded, between at 2 points, or even finding the area under the curve of, say, F. But now what we are interested in is, how do I find the area between two curves, right? So if you kind of follow my stylus up at the top, if you've ever had access to circuit board, PCB, where if you've ever had to solder or desolder something from a circuit board, then these little diagrams here, these pictures will remind you, right, but of what that looked like. But in case you haven't, it's not a big deal. So basically, what you have is some type of circuit board, and you want to be able to move electricity throughout the circuit board in certain paths, right? So that whatever you're using, whatever application you're using it for, will work. Now, if you want to move electricity around, if you're soldering, you have a few different metals that you could use. One of the best metals is gold. Now, gold is a highly efficient conductor, right? And it is relatively free from corrosion, right? So in other words, you can get a lot of cycles out of that metal. Again, a lot of it has to do with how the thickness used, et cetera, but if you were to take some of this gold plating here on the circuit board, the thickness is it's I wouldn't say it's inconsequential. It's not negligible, but it's something like 300 microinches, right? So if you were really trying to calculate how much gold you would need for, say, this particular circuit board, you could, if you would like, you could hold the thickness constant for just a second and focus on the spread, right, on the area. But in a scenario like that, if you were trying to, you can just imagine you have a spread of gold here, a spread of gold here. If you're trying to add up all of these areas, right, to get a feel for how much gold plating is going to be used, well, you have your work cut out for you, right? So, but how would you go about that? Well, if you take a look at a diagram like this, we can start to think about these traces as lines and curves in a plane, right? And if you can think about these traces as lines and curves within a plane, then you can model them, right? There, you could find an equation that would model these curves. And then if you have functions, if you can model functions, then you can use these techniques of calculus, right? So again, the goal is to be able to find the area between two curves. Now, you can imagine that if I were to take the area, the entire area under F, right? Obviously that's larger than the area that we're interested in. But if I were to take that entire area and then subtract out the area that we are not interested in, what you would be left with in that case, what you would be left with is the area between those two curves. So that is what you're seeing in this scenario. So notice that we're using definite integration. We're integrating from A to B. Only this time, we're going to be subtracting out that difference, right? So we imagine this formula as, let's find the area under F, right? So that's all of this, minus the area under G, which is all of this, and that will give us the desired result, which is the area between the two curves. So I believe that is intuitive enough that I don't have to elaborate on rectangles and etc. on how we can proceed forward. But this is the formula that we're going to be using, right? This is the formula for finding the area between two curves. And I'm going to try to help you out for a second. So notice that it's f of x minus g of x within the integrand. That is not a good way of thinking about it. For right now, I'm going to be slightly informal, but this is going to help you. It's much better to think about this as the top curve minus the bottom curve. I'll say that one more time. So if I were, so obviously looking again at our picture, the given from A to B, I think you would agree with me, from A to B, the F curve is, throughout that entire interval, is on top or higher, right, than the G curve. So in that case, it would be the top curve minus the bottom curve. But do you see how I could trick you? If I wanted to, on a test, I could call this curve F, and I could call this curve G, because it doesn't matter what I call it. And then a student could, grab their formula sheet and say, oh, well, it's just f of x minus g of x, and so f minus g. You can get yourself slightly confused. So that's why I offer this as a way of thinking about it. But let me read our definition here. So we have to assume a few things. Right, first off, we have to assume that our two functions are continuous. Right, so let's take it like f. So I can draw f from A to B without ever lifting my stylus. Right, so it's continuous. This doesn't work if you can draw and then you have to lift your pen and then draw. So it has to be continuous from along the interval A to B. Now, really what this is saying is that the g of x function, the g of x curve, is less than or equal to the f of x curve as throughout that entire interval. Okay? There has to be one on top, one on bottom. I hope that makes sense, right? How are you going to find the area between two curves if there's no space between the two curves? So one has to be below the other. And then what they're saying is, then if that's the case, with those conditions in mind, the area of the region bounded by those graphs, F and G, and then of course you can imagine you have a vertical line moving through A and a vertical line moving through B. Once we have those assumptions, then this is our area formula. This is our definite integral formula that we're going to be using. So let's jump in. Let's jump in and start with this question. And now I'm going to read, and then I'm going to cheat a little bit. We're going to be slightly spoiled because I'm going to go ahead and show you the graph, and the graph is going to give a false sense of ability because the graph is going to tell you which is the top curve and which is the bottom curve. But let's go ahead and get started. So we want to find the area of the region bounded by the following two graphs. So we have y is equal to x squared plus 2, and we also have the graph of y equals negative x, as well as x equals 0, x is 1. Let's go ahead and make sure we understand what that's saying. So here's the graph of x squared plus 2, and of course here's the graph of negative x. You also have to assume that you notice that we're starting at 0 and we are proceeding to 1. So there is I'll go ahead and draw that, a line, vertical line at 0, as well as a vertical line at 1. Right? I mean, the vertical lines are important because if you want to find area, you got to bound something, right? You got to if you don't, without these vertical lines, then you just have an infinite area. So what we want is the area between 0 and 1 bounded by these two graphs, right? So we want all of this area. Now, again, if you were not given the graphs, if you were only given the equations, the functions, which one are you going to call f and which one are you going to call g, right? So notice how we're not calling this f, we're not calling this g. You need to determine which one is the top curve, which one is the bottom curve. So the area formula is going to be, we're going to be going from A to B, and we need to decide which one is our f of x, which one is our g of x, so that we can integrate. Okay, so we have the graph. There's no need to spend any more time on this. It appears that from 0 to 1, x squared plus 2 is greater than negative x. So we now know what we have to label f, what to label g, and at this point we're gonna substitute, right? So we're gonna substitute f of x, we're gonna substitute g of x. We also need to substitute our bounds, right? Remember, this a is the lower bound, so we're starting at 0 and we're proceeding to our upper bound, which is 1. So the 0 is here, the 1 is here. Let's go ahead and write that out. So we're going to be integrating from 0 to 1, and we got x squared plus 2. Okay, now be careful. This minus symbol is already there. Okay, it's f of x minus g of x. So I'm going to write that minus symbol. It's already there. And then let's go ahead and substitute g of x, which is negative x. Okay, so let's go ahead and drop those brackets and combine, right? So this is going to be x squared. We have minus negative x, that's plus x. So we got x squared plus x plus 2. All right, so this is super simple integration, no tricky stuff. This is just power rule, power rule, power rule. So what we have is, start with x squared, so if we add 1 to the exponent, so x cubed over 3 plus x squared over 2, and if you integrate 2x, you just get, 2, you get 2x. All right. At this stage, it's going to be f of b minus f of a, right? That first fundamental theorem of calculus. So at this stage, we're just backstubbing. We're going to plug 1 in for x here, for x here, for x here, minus plug 0 in for x here, here, and here. And what you get is, at that point, you get 1/3 plus a half plus 2, which adds up to be 17 over 6. This is the answer, right? Don't give me decimals. Don't give me approximations. If you give me approximations, I'll take off points. Give me the actual result. All right, so not bad, right? I think you'll agree with me. That's not that bad. Let's go ahead and look at example 2. So we want to find the area of the region bounded by the following 2 graphs. So we obviously need to figure out which is the top curve, which is the bottom curve. Now, in a little while, in just a little bit, probably at in the next video, I'm going to talk about, are you integrating with respect to x or are you integrating with respect to y? Because if you're integrating with respect to x, it's top minus bottom. If you're integrating with respect to y, it's going to be the left curve minus the right curve. So let's stick with top minus bottom. Let's stick with dx. So clearly, one of the first things we're going to have to figure out is which one is f of x, which one is g of x. In other words, I don't care. Listen to me. I don't care what this says. The real question is this the top curve and is this the bottom curve? Okay? So please keep that in mind. Okay, the next thing, can you notice what's the difference between example 1 and example 2 is they don't tell you the bounds, right? So let's go ahead and take a look at our geometry here. So let's assume for a second that you were to plot 2 minus x squared, right? And you were to plot y equals x. Do you see how you don't know at this point? You don't know if you want the area between the 2 curves. You don't know the x values yet, right? You don't know, when you set up your integral, you don't know your upper or lower bounds. Let me rewrite that. You don't know these. So how do we figure that out? Well, I think you'll agree with me that these bounds are just the points of intersection, right? So we need to figure out the points of intersection between these 2 curves. All right, so we want the points of intersection. And that's going to help us set up our bounds. Well, easy enough. We're just going to set them equal to each other and solve for x. So we're going to set f of x equal to g of x, and then we're going to solve for x. So that's 2 minus x squared is equal to x. Okay. So we got to be able to solve for x. Let's go ahead and set this equal to 0. Right? I'm going to do 2 things at once. I'm going to take this x and bring it over to the left side so that this right side's equal to 0. And I'm also, once I bring this over here, I'm also going to rearrange the terms, right? So I would have negative x squared minus x plus 2 equals 0. All right, well, hopefully this factors. If not, I'm going to have to use the quadratic formula. I'll go ahead and factor out a negative, leaving me with x squared plus x minus 2. And let me make sure I did that correctly. Bear with me here. So I got a positive 2 here. If I factor out a negative, yeah, so that's right. So now I can go ahead and factor. So this is x, what is that? X plus 2 times x minus 1 equals 0. Okay, so all of that work, right, the whole setting equal to 0 is so that we can use inspection, because if I can make this factor equal 0, then by default, anything times 0 is 0, then by default this factor will be 0. So let's go ahead and figure that out. So the first question is, what would x have to be to make that first factor equal 0? Well, if x is negative 2. And then let's look at the second factor. What would x have to be to make the second factor equal 0? Well, x would have to be 1. So beautiful. That is, I don't need to figure out the y points right now, but so what we just figured out is that our bounds are from, remember, negative 2 is the lower bound, to positive 1. All right, well, it does just so happen that 2 minus x squared is the top curve, and x is the bottom curve. So let's go ahead and take f of x minus g of x. 2 minus x squared minus x. All right, so fairly easy. Let's go ahead and drop those brackets. I would have negative x squared minus x plus 2. Easy integration, just power rule. So this would be negative x cubed over 3 minus x squared over 2 plus 2x. And the only thing left to do is back substitute. Okay, so plugging, again, just plugging 1 in for x here, minus plugging negative 2 in for x here. The result would be 9/2. So that's not that bad. At least I think you'll agree with me that's not that bad. Let's go ahead and take a break, and when we get back, I'll check to see if there's anything else that I need to go over from this section. If I do, I do. I already know something else I need to tell you. So we'll pick back up in the next video.